Now let's see the steps involved in a neural network. So the steps that I'm going to explain are a very simplified approach and it can be extended over more complex problems. This is just for understanding the working of the neural network. So let's see what are the steps involved. In step 1, we initialize the weights. Let's say wij at some random values in a small neighborhood around 0. Then in the next step, we use the forward propagation to compute the activations of neurons in all the layers. That is the vectors A1, A2 up to AL. Remember the number in superscript denotes the layer. Now don't get overwhelmed by the new term forward propagation. The method that we saw earlier of calculating the activation function using neurons from the previous layer is called as forward propagation. This is nothing but a fancy name, that's it. Then we'll have to calculate the weights using back propagation such that the loss function is minimized. Now this is a crucial step and I'll be explaining this in a bit. But before that, let's see what are the other steps. Then in step 4, we will update the weight matrix for all the layers. So whatever weights we have calculated in step 3, we will use those weights and update our weight matrix using those weights. Then in step 5, we'll go back to step 2 again until convergence which is attained when improvement in the next iterate is negligible. So these are the basic steps involved in a neural network. Now as I said earlier, the step 3 is a very important step. So let's see this in a bit more detail. So in the first step, we initialize the weights wij at some random values in a small neighborhood around 0. So here weights are being denoted with wij. But earlier we used the notation as theta ij. So both are same, there is no difference in it. You can even write theta ij here. Then in the second step, we will use the forward propagation method to compute the activation of neuron in all the layers. That is the vectors A1, A2 up to AL. Now don't get confused by the new term forward propagation. The method that we saw earlier of calculating the activation function using neurons from the previous layer is nothing but forward propagation. So we have already studied this forward propagation method. Then in the third step, we will have to calculate the weights using back propagation such that the loss function is minimized. Now this is a crucial step and I will be explaining this in a bit in detail. But for now, see the next step first. Then in the fourth step, we will update the weight matrix for all the layers. And then we'll go back to step 2 until convergence which is attained when improvement in the next iterate is negligible. So we keep on doing this until improvement in the next step becomes negligible. So these are the steps involved in building a neural network. Now as I said that step 3 is a crucial step. So let's see step 3 in detail. So we use backpropagation algorithm to calculate weights. Now the goal of backpropagation is to adjust each weight in the network in proportion to how much it contributes to overall error. Basically, if we reduce each weight's error, eventually we'll have a good prediction. So while performing the backpropagation, we need to compute how good our predictions are. So to achieve this, we use the concept of loss function or cost function. Now depending upon the problem, we select the loss function. One loss function is the MC, sum of squares of the differences between actual and the predicted value. Now the next question is, how do we reduce the loss function? Because our predictions are only good if we have the optimized loss function. So to optimize the loss function, we use another algorithm which is called gradient descent algorithm. Gradient descent algorithm reduces the weights by changing it such that the loss converges to the lowest possible value. So we try to reduce the loss in a controlled way. We take small steps towards the minimum loss. This process is called as gradient descent. The equation shown here on the screen is for the loss function, and the graph given here is showing the loss function being converged to the minima in a stepwise fashion, which is called gradient descent. Here alpha is known as the learning rate and it is multiplied by the derivative of our loss function. So we have taken a partial derivative of the loss function here. Now in partial derivative, we find the derivative with respect to a particular term and keep the remaining terms as constant. So as you can see, we have taken a partial derivative of loss function. In partial derivative, we find the derivative with respect to a particular term and keep the remaining terms as constant. To calculate the partial derivative of a function, we use chain rule of derivatives. We don't have to go into the details of it. It is just simple maths. So that is how we use gradient descent function to converge a loss function to the minimum. Well, I hope this has become clear now. I have explained it in a very simple way, but in reality it is a complicated process and a lot of things happen in these steps. But this is enough for us to know. We don't have to go into more details because everything will be done by us, but we should at least know the basics and we should know how things are happening in the background. Now the next question is, how do we initiate the weights? So we initialize the weights by random initialization in a small neighborhood around 0. That is an interval of the form minus epsilon to plus epsilon, where epsilon is generally a small positive number. Then the termination or convergence criterion is when the absolute improvement in the next iterate for all the weights is less than 10 raised to the power minus 4. Then we introduce another term called momentum. So it has been observed that the step of updating weights can be made more powerful if we add a fraction of previous weight adjustment. This is known as momentum. So in our weight formula, we add a term eta multiplied by previous weight adjustment. Eta will always lie between 0 to 1. So that is how we introduce the momentum term. Now the purpose of momentum component is to move the weight adjustment to stay in the same direction, which in turn increases the rate at which the weights approach the neighborhood of optimality. So in short, momentum expedites the process of optimization.